All right, so the next thing that we need to take a look at is growth and decay factors and how you calculate these things. So growth or decay factor is calculated by setting it equal to 1 plus the rate, whatever the given rate is. Now, if you're given a rate that's in percentages, you're going to have to change that over to decimal. If you're given a rate as a fraction, you're also going to have to change that over to a decimal in order to be able to get what your growth or rate factor is. So if we're given a rate of 2%, that is equal to 0.02. So then what we're going to do is we're going to take the rate plus 1, and that's going to give us our growth or decay factor. So it's going to be 1.02. Now remember that since this is greater than 1.02, or since it's greater than 1, then that means that you have a growth factor. So this is going to be growth here, simply because this is greater than 1. This becomes your B value when you're putting it into the general or vertex form of the equation. If you have a rate of 1.5, then what you would do again is you're going to go ahead, it's already in decimal form, so just add it to 1, and then you get a growth rate of 2.5. Now, what if you have a decimal that is less than 0? So you get a negative decimal, so negative 0.47. We'll just follow the same thing, 1 plus negative 0.47. So you're subtracting 0.47 from 1, which is going to give you 0.53. What this tells you is that because that is below 1 but greater than 0, then what you've got there is a rate of decay rather than a rate of growth. So again, remember that whenever you're working with growth and decay, if you have a growth rate, that's going to give you a value that's above 1. If you have a decay value, then that's going to give you a value that is below 1 but above 0. The first word problem in this section is related to the amount of money spent in restaurants in the United States since 2005. And what the book tells us is that since the year 2005, the money that has been spent in restaurants in the US has grown at a rate of 7% each year. In 2005, the amount that was spent was $360 billion. So what it wants us to find out is how much money would have been spent in American restaurants if that trend had continued through the year 2015. So what we've got to do is we've got to set up an exponential model. The model that we're going to use is y equals a times b to the x. This time, a is going to represent our initial amount. B is going to be our growth or decay factor. So what we've got to do with this is we've got to go ahead and set up an equation that uses that given information and the information that we figure out for ourselves. So we get y equals 360, and we're going to use 360 in billions. So 360 times b, which is going to be our growth rate or our decay rate. So we're going to go 1 plus, and then what is our rate? Our rate is positive 7%. So that's going to be plus 0.07 to the x. So our new formula is y equals 360 times 1.07 to the x. And what we want to do is we want to figure out how much would have been spent in 2015. So that's 10 years down the line. So we're going to replace this x with a 10. Now you're going to have to go into a calculator and then plug all this into a calculator. And when you do, you're going to find out that this is going to be approximately $708 billion that would have been spent in the United States in restaurants in the year 2015 if the trend that had started in 2005 had continued. In problem number 2, we're given a scenario in which your friend was gifted $2,000 by his parents on his birthday. What they did was they took that $2,000 and put it into a savings account on the day that he was born, and that savings account is going to yield 4.5% interest compounded quarterly. So we're going to consider that the day that he was born as year 0, and we want to find out how much will he have in that account at his 18th birthday. The formula that we're going to use for this is A equals P times 1 plus R over N to the NT. And the A, or A of T, is going to be the amount at a particular point in time. The particular point in time that we're looking for is that 18th birthday. So it's going to be A of 18 equals the principal. How much was put into the account initially? That was $2,000. So we're going to replace P with 2,000. Then 1 plus R. R is going to be our rate, which was 4.5%. So change that into a decimal, 0.045. Then divided by the quarterly. Quarterly means 4. So we're going to divide by 4. And then we're going to have raise it to the NT. So the N is 4 and the T is the 18 years. So now we're going to simplify this a little bit before we put it through the calculator. We get 2,000 times 1 plus 0.045 over 4 to the 72nd power, because 4 times 18 is 72. Now, when you put this through the calculator, and you're going to need a calculator to do this, you're going to end up with that on his 18th birthday, there will be $4,475.53 in the account. So over those 18 years at 4.5% interest, he gained an additional $2,475.53 in addition to his original $2,000 deposit. In problem number 3, we're given the atmospheric pressure in kilopascals at sea level. And the number of kilopascals at sea level is 101. Then every time that you go up 1,000 meters in altitude, you're going to lose 11.5% of that atmospheric pressure. So the question is, what is the pressure at 3,000 meters? We're going to go ahead and use this exponential model to answer this question. So we got y equals a times b to the x. Now our initial pressure is 101, so this is going to be our a value. So y equals 101. But then for b, we've got to find out what our growth or decay rate is. So we're going to go 1 plus, and then we've got negative 11.5%. So 1 plus negative 0.115. And then our x is going to be 3,000 meters, but we're looking at minus 11.5% for every 1,000 meter increase. So if we go up 3,000 meters, how many 1,000 meter increases do we have? We have 3, so that's going to be our exponent. Now, we just need to go ahead and simplify this down a little bit. 1 plus negative 0.115, well, that should be 0.885. And what we're going to see here is that we're going to have a decay rate because this right here is less than 1. So you're going to go ahead and plug this into your calculator and you're going to get approximately 70. So once you go up to 3,000 meters, you're going to have approximately 70 kilopascals of atmospheric pressure at that elevation.